So while Tanya was going to talk about cocktails because she at some point became a professional cook, I'm going to be talking about ices because I'm the kind of person who's always cold. That's the hat. So I also like making lots of bad puns as my fun factoid, so I apologize in advance. I'm going to give you guys the take-home message right away. Basically, I want to convince you by the end of this talk that the composition of something as basic as ices is really crucial for understanding the composition of planets that form around young stars, and ultimately the ices form the building blocks for life as we know it on our own system, but also potentially in other systems around other stars. All right, there, okay. So life as we know it ourselves is made up mostly of 4 different elements: hydrogen, oxygen, carbon, and nitrogen. And at first, you might look at the surface of Earth and you go, well, that's fantastic because we see a lot of those elements in materials that are on the surface of Earth. We see water, we know we have way too much CO2 in our atmosphere, so all those elements are checked, we're good. But actually, we know if we take into account the entire mass of Earth, including its mantle and core, that really the Earth is 99% rocky elements. And oxygen is included in there because oxygen can be both a rocky element and also an icy element. But most of the material that we need for life is only located in this very thin skin on the surface of Earth. And we think, looking at things like how heavy specific elements are, that actually these materials were brought to Earth potentially by something like comets. So this is comet 67P that was observed in the mid-2010s. And it brought a lot of material to, comets like this may have brought a lot of material to Earth, including simple ices like water and CO2, CO, methane, and ammonia, but also more complex molecules like methanol, ethanol, and acetaldehyde. And just going forward for the rest of the talk, remember methanol is the poisonous alcohol, ethanol is the good alcohol, and acetaldehyde is the thing that gives you a hangover the next day after you've had too much ethanol because it's metabolized in your body to make acetaldehyde. So all of these complex species are things that could potentially react to form other molecules that are actually important for the formation of life eventually. And on top of that, they give the basic ingredients in terms of these elements that can support life on Earth. So if we want to understand whether other star systems or planets in other star systems get these basic ingredients, we need to find a way to study simple and complex ices in other systems. Now, ices form initially in dense molecular clouds, like Tanya was saying earlier. This is an example of the Pillars of Creation, a picture that's really famous from the Hubble Space Telescope. Now, within these clouds, there are these denser prestellar core regions. This sets the T=0 moment of star formation. These dense regions collapse to form a central protostar. That central protostar has material that feeds into it from the molecular cloud. Over time, about 1 million years or so, that material in the cloud sort of gets blown away from this protoplanetary disk, and you're just left with this disk of material spinning around the central star, and this is the disk in which planets form. So planets form at this stage, and eventually over the course of several billion years, we end up with something like the solar system with this comet and Earth orbiting around it. So if we want to understand the composition of comets and planets like Earth, we have to trace back the ices all the way along this formation pathway back to where they originally formed in this dense molecular cloud to understand what they're made of. So we can do that, observationally speaking, by looking at stars that are located behind the molecular cloud. So these stars are very hot, and they provide sort of a continuum in the background. And then the ices that are in the cloud provide a sort of cold foreground screen that actually absorbs this background material. And what happens is the ices within the cloud will, within the molecule, the different atoms in the molecule have different characteristic motions. So in this particular case right here, you can see we have a water molecule and there's this oxygen with the two hydrogens and they're stretching away from the oxygen molecule. Sort of like if I didn't have the microphone, I'd be doing a little dance here. You can consider yourself lucky that I have the microphone. So all of these motions can actually form a sort of fingerprint that you can detect in infrared light. So if you put your little telescope here and you see these motions, this stretch right here shows up as a deep feature around 3 microns, a particular wavelength. And other ice species, including CO2 and CO, have also very deep features at different wavelengths. So if you get a large enough span of wavelengths, you can actually get a unique fingerprint for each ice species. Now, this sounds really promising, except actually the infrared is one of the wavelengths that's very difficult to observe from the surface of Earth, because shockingly, there's water and CO2 in our atmosphere, and that makes it very difficult to tell whether or not you're detecting CO2 from an astrophysical object or from Earth's atmosphere. So you actually need to go to space in order to observe a lot of these ices. Now, we're very fortunate that the James Webb Space Telescope was launched, and it can see, or was designed to see, specifically at these wavelengths in the infrared. So this is an artist's impression of what JWST would look like as it was launching. There's actually a really cool video that you can watch of the actual launch taking place. It's a joint mission between NASA, ESA, and the Canadian Space Agency. It was a Christmas present in 2021, best Christmas present ever. It does both imaging and spectroscopy. I will be showing a little bit of both in this talk. And the mission lifetime originally was set for 5 years, but the launch was so perfect by the Ariane Space Agency that it actually saved enough propellant that it can last for 20 years. So you'll be seeing a lot more material coming out of this telescope going forward over the next 2 decades. This is the last picture, last real live picture of JWST as it was speeding away toward its orbital position at the L2 Lagrange point outside of Earth. And basically, you can see a little tiny bit of that gold sun shield right here, but it was taken by a camera that they fortuitously put on the other end of the rocket so that they would get this picture as it went away. All right. So if we want to see ices with JWST, it's good to have an observing program to do that. So I actually designed this program along with my co-PIs, Admin Bogert at the University of Hawaii and Harold Linnertz at Leiden University. Back in 2017, when JWST was supposed to launch in 2018, and it launched in 2021. So it's been a really long road to get to this point. But we designed this program to look at ices in this dense molecular cloud called Chameleon-1. So within the contours and the red stuff, you've got this dusty ridge in this molecular cloud, and then you have a bunch of protostars at each stage of star formation within the cloud. So there's a cold prestellar core, and then the earliest newborn protostar here, a younger protostar, which you can see here in this picture, and then a protoplanetary disk at this stage. So by observing this region, we can actually study the total ice evolution in the system. All right, step on the board. So that was the goal of our program. And in addition to, so we plan to do this by getting spectroscopy in the infrared for all of these different objects. But in addition, we got some really nice pictures too. So if you focus on where this rectangle is, we have our first results paper that came out last January, and it basically produced this image, in addition to all the spectroscopy that we have of the ices. Just to walk you through what we see in this image, there's the invisible newborn protostar, which is located there. Again, you can't see it, but this little thing that's sticking out from that is actually a jet coming out of that protostar. Then there's the really spectacular more mature protostar that you can see with these outflows that are really wide and sort of going out like that. And there's like 700 random galaxies in this picture. The quality of JWST is so good that not only do we get all the background stars we wanted to see, but we get these random galaxies, which is pretty cool. Now, our actual science target in all of this for the first paper was this little bitty star right here. It's sitting behind the molecular cloud, but it's kind of near this, this denser part of the cloud where this invisible newborn protostar is. And we wanted to look at all the ices in this. When we do that, we can see basically all of the ices that I showed you on the previous slide. So water, CO2, and CO. But in addition, we can see a lot of minor ice species that are a little bit, I won't say complex, but less simple than these. So you can also see methane and ammonia over here. And you can also see the simplest alcohol that Tanya talked about, methanol. Remember, that's the poisonous bad alcohol. So you can see that at these two wavelengths. So what we did with this was we wanted to look at how the ices were evolving and forming in that cloud. So Tanya's gonna give me, she's giving me a dirty look here because this is like not what the modelers want to think about. This is very simplified because I'm an astronomer. But pretend for a minute that your dust grain is spherical, because we're all mathematicians and spherical cows and all that. Your dust grain is spherical, and it looks like this gum ball. So instead of the gum at the center, you have a silicate core, a little crunchy. You have some refractory carbon around that, and each one of these colors is actually a layer of a different ice species moving out from that. In reality, the ices are a little bit mixed, but basically this is more or less what we think happens. You have a water-rich layer, a CO-rich layer, and then an alcohol-rich layer on top of that. And as you go from the inside to the outside, your species get more complex. So if we take this picture and actually put the real science image here, this means that you have, again, this water-rich layer at temperatures that are about 20 Kelvin, which is very cold, but for the purposes of this diagram, it's the warmest thing you're going to see. Then you have the temperature in the molecular cloud drops a little bit, and you have a frost on the surface of your grain where you have carbon monoxide freeze out onto the grain. And then you have the temperature gets a little bit colder, you get a little bit denser, and on top of that, you have an alcohol-rich layer that starts to form on the surface of your grain. So what we did, this is the traditional view that we have of how ices form on grains. But we actually looked at the alcohol that we saw in that spectrum that I just showed you. And because JWST is so technically fabulous, you can get a really distinct shape to the ice feature. It's not just like a simple blob. It actually has some structure in it. Sorry, that was not the way I wanted to go. Okay. All right, so you can see this is an ammonia feature here, this dip. And then this dip over here is the alcohol methanol band. And there's two different components in this band. And one of the components, the one here in purple, this is the methanol that formed in the way that Tanya just described in her talk, by adding hydrogen atoms on top of this carbon monoxide until you form something that's much more complex. And that was what we expected to see. But then it turned out that we saw additionally this orange component here. And that orange component is actually methanol mixed with water. And this wasn't really expected. Well, Tanya expected it because she actually did a paper on this before the JWST launched. But the rest of us didn't really expect it. And this means that there's a different pathway to form methanol that's not the traditional one. And if you want more information about that, I'm going to turn this back to Tanya because we've been tossing this like a hot potato the whole evening about who's going to tell that pathway. But basically, this was totally new. And it means that you can form things that are pretty complex, like alcohols, already in this earliest stage. And this potentially means you can eventually reach a level of complexity in the ice, which is more than what we thought we could do before, which could be good for forming life in the future many years later. So additionally, besides the methanol, we actually found ethanol, the good alcohol, and acetaldehyde, the hangover chemical, as well. So if we look at this spectrum, again, it's the absorption depth on the y-axis and the wavelength on the x-axis. These two colored bands, the yellow one represents ethanol and the blue one represents acetaldehyde. So I realize they look just like wiggles, but we see them in 3 different spectra, and this is a pretty good detection by astronomical standards. So we see alcohol in the cloud. Now, there. That means that our picture of how the ice forms on the grain is not this simplified, gumball picture. It's more like this picture that I found on the internet, where these guys genuinely chewed a whole bunch of gumballs and stuffed them all together to make this horrible mix. You can find anything on the internet.
How did you search for that?
You search for chewed gumballs and you get a lot of really disgusting pictures. It's bad. But they have an entire YouTube channel doing this. So knock yourself out after this. This only ends at 10 o'clock, right? So this means that it's a little bit more complex than we thought. And that the implication that this has for planet formation is that in our initial picture where we have this very simplified structure, we might have a protoplanetary disk where you would start out having this very simplified dust grain that has this gumball structure, and as you move closer in toward the star, your temperature starts heating up. And because your temperature is heating up, you have a series of what we call snow lines, or locations where your ices come off of the grains and sublimate into the gas phase. And they go in a sequence, again, from the ones that sublimate at the lowest temperature to the ones that sublimate at the highest temperature, like water. You've probably heard of the water snow line in the context of formation of something like Jupiter. Once you sublimate all your ices, then you can basically destroy the rest of your rock, and then you end up in just gas that's on the central star. And this sort of structure is supposed to explain why some planets, like the Earth, are poor in carbon, nitrogen, and oxygen because they formed inside of the water ice snow line. But other planets, or comets, like Comet 67P, are rich in carbon, nitrogen, and oxygen because they formed out around the CO snow line, for example. So that's our traditional picture, but if we have instead of having this gumball-shaped grain, if it's like the chewed gumball, that means that all of these snow lines sort of get mashed together toward the water ice snow line, and that means that it's possible to have a pileup of carbon, nitrogen, and oxygen-rich material in the inner part of the disk. So you could actually get an enhancement of ices relative to what we would expect otherwise. Now, this could explain why we see that actually some of our gas giants are enhanced in ices by about a factor of 10 relative to the solar value for carbon, nitrogen, and oxygen, like in this picture of Uranus. This is a picture that was taken with JWST's NIRCam camera, where you can see Uranus itself with all of its rings and all the different moons around it, or not all of them, but the brightest ones. And basically, having this kind of mixed ice could maybe explain why Uranus appears to be very, very enhanced in its ices. But even if that doesn't, even if the mixed ices don't impact planets in exactly this way, we can definitely say that we are actually seeing in our ices the ingredients for exoplanet atmospheres. So cloud ices directly end up in exoplanet atmospheres. This is a spectrum. Brightness is a function of wavelength of an exoplanet, also observed in JWST. And again, you can see water, carbon monoxide, carbon dioxide, and even sulfur dioxide, which we also see in the ices. So the takeaway message here is that the details of how the ice form actually dictate something about the planetary compositions that you get over the next million years when you form planets out of these clouds. We've got a lot to learn, but JWST is enabling new discoveries right now as we speak. And the subtext of this whole thing, which you waited for, there's a lot of alcohol in space, including the drinkable kind, but you're going to get a hangover because there's acetaldehyde too. So, thank you very much for your attention.
Questions for Melissa? I mean, these observations, these spectra are recorded with JWST. How long does that take?
In the case of this, should I go back. Right. This took about 1 hour of integration time. So the telescope was parked on this target for 1 hour. Let me rephrase this. This half took 1 hour and this half took another hour. Because there's two different instruments. There's MIRI, which is the long wavelengths, near spec, which is the short wavelengths.
Right. But so for 3 spectra, you're like 3 hours and it's done. That's really that simple.
Yeah, so the downside is you get one spectrum, like one object in 3 hours. If you do the math on like 20 years, that's still like not that many targets. There are other modes where you can actually get multiple targets at the same time. And if you're really clever, you can set it up. And I was not really clever because you need to know in advance the very detailed position for the target in order to use this mode. And we had coordinates, but they weren't to the precision that was necessary.
Does that mean use it? Or how does this work? Like,
there's a piece of
is
software.
Is there someone sitting at a computer controlling the thing, or are you? Or?
So there's a piece of software called the Astronomer Proposal Tool. So I use that software to set up the observations. It gets sent into the Space Telescope Science Institute, which is the institute that controls the telescope.
Yeah.
They have someone double check to make sure I didn't F anything up royally, because it's a very expensive observatory.
Sure.
And then they have someone upload a series of pre-programmed instructions to the telescope, and it will, in a totally non-transparent scheduling piece of software, schedule everything and observe it. Yeah. But there are definitely checks to make sure that the $9 billion telescope is not pointed at something that could destroy it, if that's where this was going.
It wasn't, but...
But it's good to know, nonetheless, right?
Can I ask a question? Several times in your presentation, you said a sentence that goes something like this. You have this molecule, and you have this molecule. I want to ask, and you presented it as like stages for something, as a process. What do you really mean by you have this molecule? You have is this the result of an observation or a calculation, theory?
Okay, so for this is the result of, there have been previous infrared space missions. There was the Spitzer Space Telescope that launched in 2003 and went until 2008. There was also the Infrared Space Observatory, which was mid-90s. So they got, for a handful of objects, the kind of observations that we had, just not as good quality. So like, instead of seeing all of these ices, they maybe saw water, CO2 and CO, and maybe the silicates, but not the rest. Or in a few very bright objects, they may have gotten methanol and some of the other weaker bands. But it was really for like a handful of objects. So on the basis of a handful of objects, because we're astronomers, we went to the chemical modelers and like, hey, we see these things, tell us why we see them. And Tanya was still in high school, so it wasn't her, but other people, okay, maybe undergrad, sorry. And actually like put together this schematic of saying, okay, if we see these few things, how can these fit together in a puzzle piece? But now that we have a much bigger picture, then we can actually go back and question the assumptions that went into that puzzle piece.
Cool, thanks.
Yes.
So you're using your ice observations to say something about the planet atmospheres or check them with the planet atmospheres. You also go the other way around and you look at the planet atmospheres and you think, what kind of ice should we be seeing that we're not seeing?
Yeah, so you can, but the thing is that because the planets have been heated up so much, it's hard to make a one-to-one, water is such a basic and simple thing that you can go like, I'm drawing a straight line between this cloud and that planet. But if you see, like for example, we see this, I can't go through this fast enough probably. We see the sulfur dioxide in the ice and in the planet, But sulfur can also be carried by other species like iron sulfide, for example. So it's not necessarily, that's why this one is circled in pink, because you could have maybe some chemical reactions on a different sulfur carrier that reacted with some oxygen to produce this. And that's something that is actually like really an active area of research, as Lars knows, because he just did that with Tanya for a project. Something like that.
All right, if that's it, thank you, Lisa again.